Now let's draw what we would expect the orbital interaction diagram to look like for diatomic boron. An orbital interaction diagram shows the relative energies of the atomic orbitals and then the molecular orbitals to which they give rise when the atomic orbitals overlap. So for each boron atom, on each side here, for boron A and boron B, I've drawn the valence atomic orbitals. So the valence atomic orbitals are of course, the 2s orbitals. These are the 2s orbitals, which are lower in energy than the 3 degenerate 2p orbitals. So these are the 2p orbitals for each boron. Now, boron is in the second row of the periodic table. It has 3 valence electrons. So I'm going to use Aufbau's principle and Hund's rule to fill up the atomic orbitals of boron. And this is just like what we did way back in chapter 2. So that here's each boron atom with its 3 valence electrons filling up its valence atomic orbitals. Now, what happens when those atomic orbitals overlap? Well, we saw that the 2s orbitals overlap very constructively to produce what we called the sigma 2s orbital. This is a bonding molecular orbital that is lower in energy than the atomic orbitals that give rise to it. Equal and opposite would be the sigma star 2s orbital. This is the anti-bonding orbital that's higher in energy than the atomic orbitals that give rise to it. So we have the sigma stabilized MO and the sigma star destabilized anti-bonding MO. We would also expect that when the 2px orbitals overlap on boron, that we would get the sigma 2p molecular orbital, that kind of stabilized molecular orbital with the orbital density along the bonding axis. And then when we had the 2py and the 2pz orbitals overlap, we get 2 pi 2p orbitals. So these would be bonding pi 2p molecular orbitals. Then equal and opposite to those, we would have the 2 pi star 2p orbitals that are higher in energy than the valence atomic orbitals of boron. And then the highest energy molecular orbital would be the pi star 2p orbital. So you notice that the destabilization of that one is predicted to be equal in magnitude but opposite in direction to the sigma 2p bonding molecular orbital. So this is what we would expect the atomic orbitals to look like for diatomic boron. Now, let's take those 3 plus 3 equals 6 electrons, those 6 valence electrons from the 2 borons, and we can fill up the MOs according to Aufbau's principle and Hund's rule. So we have 6 electrons, 1, 2, 3, 4, 5, 6, 7, 8. Oops, too many electrons, right? I only have 6 to fill. So that is my bad. I just counted wrong. Each boron brings 3 electrons to the table. So 3 plus 3 is 6. Okay, so 2, 4, 6. I start with the lowest energy molecular orbital, and then I keep going up, pairing as I go up. So this would be the expected molecular orbital diagram for boron. Okay, now of course I'm going to tell you that this is not actually the case. Why? How do we know? Well, if this MO diagram were correct, all of the electrons are paired, right? We can see that the electrons are paired in the sigma 2s, sigma star 2s, and sigma 2p. So if this MO diagram were correct, the B2 molecule would have all of its electrons paired. However, experiments have shown, so this is a big however, experiments in the lab show that the B2 molecule is actually what's called paramagnetic. So this is a new vocabulary word, paramagnetic. What does it mean? Paramagnetic means that when you do an experiment where you put the molecule into a magnetic field, if it has unpaired electrons, it's going to be attracted by the magnetic field. So this is attracted by a magnetic field. And then that only happens when the molecule has unpaired electrons in it. So how can this be the case? We just drew the orbital interaction diagram for B2 and all of the electrons are paired. So this experimental evidence shows us that there is this odd inversion between two of the orbitals. The inversion occurs here among the sigma 2p and the pi 2p orbitals. Okay, so let me show you that one more time. We have the inversion occurring here. So the actual order for the energies of the MOs for boron is going to be as follows. And I'm just drawing the middle part of the orbital interaction diagram. So we start with sigma 2s, then we have sigma star 2s, then we have the two pi 2p's. So this is where that unexpected inversion occurs, followed by the sigma 2p's. Then we have everything else as expected, the two pi star 2p's, and finally the one sigma star 2p. So these are all the molecular orbitals, and this would be the energy scale on the y-axis here. So this accounts for the paramagnetism of boron, because if I fill up those 6 electrons now, and I'm using Hund's rule, these 2 electrons end up being unpaired. So this explains the paramagnetism of boron. It has these 2 unpaired electrons in the pi 2p orbitals from Hund's rule. So in the next lecture, we'll talk about which homonuclear molecules have those orbitals inverted.